In 2025, SpaceX didn't just launch more rockets, they upended decades of spaceflight assumptions overnight. Starship tests moved from risky prototypes to repeatable systems, while engine upgrades and a relentless launch pace set new global records. Just as critics thought the limits were set, the reality was even more dramatic. A single year that forced NASA and every rival to rethink the rules. How did SpaceX accelerate decades of progress into 12 months? And what broke open the path to human missions far beyond Earth? At Starbase in 2025, the pace of hardware assembly reached new territory. Booster 19's build unfolded with a speed that left even seasoned trackers surprised. Its stacking advanced far faster than Booster 18, a clear sign that SpaceX's production flow had matured. This acceleration was not luck. Behind it stood a series of tangible changes on the factory floor. In the Mega Bay, crews worked with larger steel panels and a reduced number of weld seams, a move away from the patchwork of smaller rings and joints that once defined early Starship builds. Fewer seams meant not only less time spent welding, but also fewer opportunities for leaks and inspection delays. Ship 39, representing a more refined Block 2 generation, carried these advances forward. Its hull showcased larger, vertically oriented panels joined by long welds, crafted with improved automation and precise alignment. The result was a cleaner, more robust structure that demanded less rework and could be assembled with greater consistency. This was not just about speed for its own sake. Every hour saved in assembly translated to more frequent launches and faster data return for engineers. The shift from experimental, one-off prototypes to hardware designed for repeatable, reliable production was now visible in every weld and every stacked ring. Factory teams, drawing on lessons from earlier delays, coordinated around the clock to keep the flow moving. By late 2025, Starbase's expanded bays and new tooling had transformed super heavy assembly into a process measured in weeks rather than months, laying the groundwork for a cadence that would soon test the limits of what even SpaceX thought possible. Starship's transformation in 2025 was about more than just speed or assembly. The underlying mission architecture was quietly being rewritten. For the first time, hardware rolling out of Starbase was engineered with orbital refueling as a central requirement, not a distant goal. This was a direct response to the demands of NASA's Artemis program, which relies on Starship's ability to transfer propellant in orbit to reach the lunar surface and return. Block 2 Starships incorporated increased propellant capacity, revised tank geometries, and reinforced docking interfaces, all designed to support the choreography of multiple ships linking up in low Earth orbit. NASA documentation throughout 2025 emphasized that future Artemis landings would hinge on a series of Starship tanker flights, each delivering liquid oxygen and methane to a waiting depot ship. While no full-scale refueling demonstration flew in 2025, the test flights validated the structural and avionics upgrades that future tanker missions will require. The new interstage designs, vented plumbing, and avionics suites underwent real-world stress during coast phases and engine relight attempts, building confidence for the next phase. SpaceX leadership openly described the upcoming Starship version as the platform that would finally attempt in-orbit propellant transfer. By late 2025, every design decision from tank volume to docking hardware was shaped by the needs of lunar architecture. The shift was not just technical, it was strategic, embedding refueling capability into the DNA of every new vehicle. This architectural pivot set the stage for Starship to move beyond single-shot flights and become the backbone of sustainable lunar and Mars missions. At the McGregor Test Facility in August 2025, teams gathered around the vertical stand as the latest Raptor 3 engine roared to life. This was not a routine hot fire. The goal was to push the new design to its limits, with longer burn durations, higher thrust, and most importantly, reliable reignition. Each test cycle brought engineers closer to the target: 280 tons force of sea-level thrust for the standard version, and 306 tons force for the vacuum variant. These numbers weren't abstract. They defined how much mass Starship could carry, how quickly it could return to the pad, and how ready it was for deep space missions. Throughout August, McGregor logged a series of relight trials. On August 11th and again on August 27th, Raptor 3 engines completed multi-burn sequences without a single restart failure. The data showed not just peak thrust, but stable chamber pressures and consistent ignition after simulated coast phases. This level of reliability under test conditions was essential for rapid Starship reuse and for complex missions that would require engines to relight in orbit, such as deploying satellites or preparing for a lunar descent. Raptor 3's design eliminated the external heat shield used on earlier models, removing mass and simplifying refurbishment between flights. Engineers monitored turbine temperatures, fuel flows, and structural loads in real time, using dense telemetry to catch any anomaly before it could threaten flight hardware. By late summer, the test campaign had qualified dozens of engines for flight, each one capable of supporting Starship's push toward higher cadence and heavier payloads. For the first time, propulsion was no longer the limiting factor. The engine room had caught up with the ambitions of the vehicle. Falcon 9's rhythm in 2025 set a new standard for what a rocket fleet could accomplish. The launch pads rarely sat idle. Boosters were turned around in days, not weeks, fueling a relentless tempo that saw 165 Falcon missions lift off over the year. Each flight was a display of practiced choreography, recovery teams stationed at sea, drone ships positioned with precision, and ground crews ready to refurbish hardware almost as soon as it touched down. This was not just about numbers. Behind every successful landing stood a network of specialists tracking booster health, logging flight data, and swapping out components with the efficiency of a pit crew. Some boosters flew 7, even 8 times in a single calendar year, racking up lifetimes that once seemed impossible for orbital-class rockets. The result was a flawless streak of landings, each one reinforcing the reliability of the system. Starlink deployments made up the bulk of these launches. By December, over 9,000 satellites orbited above, blanketing the planet with low-latency coverage. The scale of this operation required a fleet-level mindset, each Falcon flight supporting not only its own mission, but the broader vision of global connectivity and rapid Starship development. Mission Control operated as a nerve center, managing simultaneous launches, coordinating recovery, and feeding lessons learned back into the system. With Falcon 9 as the backbone, SpaceX built an ecosystem where rapid reuse and high-frequency launches became routine. This operational foundation allowed Starship's ambitions to grow, while the demands of such cadence pushed infrastructure to expand in ways that would have been unthinkable just a few years before. Mega Bay's expansion in early 2025 doubled the available floor space for Starship integration, bringing parallel assembly lines under one roof. By summer, Giga Bay came online, supporting the construction of multiple Super Heavy boosters and ships at once. Pad 2, rebuilt with new chopstick arms and advanced flame trench systems, handled higher launch rates and enabled faster turnaround between flights. The demolition of Pad 1 cleared the way for further upgrades, while new air separation units at both Texas and Florida sites pushed propellant production to record levels, over 1,200 metric tons per day at Starbase alone. These infrastructure gains turned what had once been bottlenecks into strengths, allowing the production teams and pad engineers to keep pace with the relentless launch tempo. The result: hardware moved from final weld to launch pad in weeks, supporting a cadence that kept Starship and Falcon 9 launches flowing without interruption. December brought a different kind of milestone to Starbase. Instead of a launch countdown, engineers and local families gathered beneath strings of lights for the annual holiday parade, a tradition that had grown alongside the rockets themselves. The crowd cheered as teams rolled past, some in silver flame-retardant suits, others waving from flatbeds decorated with model boosters and handmade banners. For many, this was the first year their work had touched every launch. Welders, software leads, and technicians all played a part in the year's record cadence. On the factory floor, process changes filtered into daily routines. New checklist protocols, introduced in the fall, replaced old shift rituals. Each handoff now included a real-time review of sensor data and automated quality checks. These small but meaningful changes shaped a culture where every improvement, no matter how technical, was celebrated by the people who made it possible. The energy that powered Starbase in 2025 came not just from methane and oxygen, but from the pride and camaraderie of a workforce that saw their efforts reflected in the sky. SpaceX's 170-plus launches in 2025 set a new global pace for space access. As private innovation rewrites the rules, the boundary between science fiction and reality blurs. The challenge now isn't reaching orbit, it's deciding how we use that access. The next choices shape all our futures.